Hello and welcome. In this video we'll review briefly the equilibria of weak acids, and then I'll take it through a problem to calculate the percent ionization of weak acid. So here all on one slide is the brief review of weak acids. So we abbreviate weak acids HA. Remember, they are proton donors. So HA is in equilibrium with A minus, the conjugate base, and the equilibrium constant is Ka, where A stands for acid, and that's going to be products over reactants. And remember again that water is liquid. It does not enter into the equilibrium expression. So for our first example, we want to write the equilibrium reaction and expression for lactic acid. So step one is to basically look for your table of weak acids and weak bases and find lactic acid. Okay, and then the template, remember, is to add H2O and then use the equilibrium arrows and write the conjugate base and H3O plus on the right hand side of this equation. And your equilibrium expression is always going to be products over reactants, and remember again, liquid water is not entering into this equilibrium expression. The Ka value can be found on that same table of weak acids and weak bases. It has a value of 1.4 times 10 to the minus 4. Remember that if you have a Ka that's much less than 1, it means that reactants are highly favored and products are disfavored. Okay, so this indeed is a very weak acid. For example 2, there's a bit more work than to just show you all on one slide the answer. We want to calculate the percent ionization for 0.20 molar lactic acid, that same acid that we've previously discussed. So you should be able to write out the equilibrium expression for that weak acid and then write down what the Ka value is using that table. Okay. What we want to do here is set up an ice table as usual. So the initial change equilibrium all on the first column, and then we write the chemical formulas of all the things involved. Okay. Now we're starting out with 0.20 molar lactic acid. That goes in the top left box. I'm just going to put a hyphen here for water. It's liquid and does not enter into the equilibrium expression, so we don't even need to worry about that. And for our products, we both assume they're 0. Now I know in pure water there is minute amounts of H3O plus present, but for all intents and purposes we're going to assume it's 0 or very close to it in comparison to the H3O plus that's formed from our lactic acid. So again, remember where you put the changes. We put the plus x's under the zeros, and we put the minus x's on the opposite side of the equation. So we're going to have minus x on the left, plus x, and plus x for our two products. And then to calculate the equilibrium, we just add up those two columns there. So 0.20 minus x and x are the final equilibrium quantities here involved in this equilibrium. All right, and now that we have all of these values figured out for the equilibrium, we switch our attention to doing algebra with the equilibrium expression. So we want to write out the Ka for this chemical reaction, its products over reactants, and then we want to substitute in those equilibrium values. So we have x for both of the products, and we have 0.20 minus x for the lactic acid reactant. Okay. We want to then go ahead and begin to solve for x. So the Ka value here I've substituted in is 1.4 times 10 to the minus 4. Okay, and we want to make the very important simplification. We assume that x is very small, and so 0.20 minus x is approximately equal to 0.20. So we can neglect that x. And then we combine terms here, so we have x squared, and then using your calculator, you can do the rest of the math on your calculator. 1.4, 10 to the minus 4, okay, times 0.2, and then you hit the square root button on your calculator, and I show that result here on this slide. On my calculator, it displays it in scientific notation. That's fine as well. 5.3 times 10 to the minus 3 is the same thing I've written here on this slide. All right, we have x. And what does x represent? X represents the amount of a minus in the ice table. You might have to go back to the ice table and kind of look at that. But the percent ionization formula from the OpenStax textbook is A minus divided by HA times 100%. So we have 0.0052 divided by 0.20. That's the starting quantity still here on this slide in the word problem. And you multiply by 100%. Sorry about that typo there. Just to move the decimal over 2 spots to give you 2.7% ionization. So 2.7% is very small. That makes this substance a weak acid and a very weak electrolyte indeed. So lactic acid is expected to be a very weak acid, okay? Here is a problem for you to try. What is the percent ionization of 0.20 molar hydrocyanic acid? So first you want to write the equilibrium reaction out, HCN aqueous plus H2O, and go on from there. And then write the equilibrium expression, which is products over reactants, and calculate the percent ionization. And then I've got a final question here. Is HCN a stronger or weaker acid than lactic acid? Remember again, if you have something with a higher percent ionization, it means it's a stronger acid. Thanks for watching. Please like, please subscribe. Have a great day, everybody.